We're going to look at the sources of variation and error lab today. So we have some notes, and then we'll go over what to do and how to evaluate the data you get from the experiment. So the first thing in this is the course homepage. So in order to get the lab handout, you can click on the Lab 1 Material Sources of Variation and Error tab. And from here you have a Word document version and a PDF document version. You can get the PDF document version printed out, write on it, scan it back in, and then upload that as your assignment, and then attach your Excel document for any kind of numerical calculation if you'd like, or upload the graph as an attachment, or you can take the Word document and fill in the values and then add your Excel sheet, or you can actually paste some of the data and kind of type up just the informational sections of the report to turn in. So you have several different ways that you could submit your report. One thing is, if you want to submit your Excel sheet as your calculations and not rewrite the values down, that's fine also. So you can download the Word or the PDF document. There's also a PDF notes and a PowerPoint available for this assignment. So the PowerPoint and the PDF notes are very similar, but the PDF notes includes a little bit more detail. So both of those are available in terms of notes. We'll go over the notes in just a minute. This layout gives you the information that should be included in your report. So as long as you have the things that are listed in the layout, you should be fine in terms of your score and being able to submit what's required for the assignment. And then this historical data with example results can be used as both an example for the assignment as well as your historical data for the question in the question sections, which is question 6, that asks for a comparison between the data you evaluate and the data to compare to. So for the on-campus class, your set of data that you'll work with is this spring 2021 on-campus or distance data. And then for the distance class, you can either use that set of data or one of the other uploaded sets of data that's available from a previous semester. So if you click this 2021 data, it should automatically download or ask if you want to download the assignment. From that, you'll see your downloaded file. So here, kind of to explain the layout for this, there were 65 cans tested total. The highlighted blue cans are the cans that were tested by the students that came for the on-campus section on Thursday in January of 2021. So these 16 cans were tested by students in the lab, and you can use this set of data as one option. And then the section that was in green are cans that I tested after the Thursday on-campus class attended, which mainly was to make a video for the students who didn't come in class, or for the distance video for spring of 2021, or just in order to have additional cans in order for the calculation and kind of just to give more values to work with. So you can do just the green cans if you'd like to work with those, or you can work with all 65. So there's 3 possibilities you can do in this set of data. So these 3 columns off to the right are those sets of data in ascending order. So the only way you would need to use the ascending order values is if you want to make your plot the numerical distribution or the normal distribution curve plot, or considering we don't know if it's going to be a normal distribution or not yet. If it's a positive or negative skew, then if you have your continuous plot graph, then you can use the ascending order one. If you want to make a histogram plot, then you don't need the ascending order values. So the reason there are 3 of these is it's in ascending order for the extra cans, the on-campus cans that were just tested by the students who came for class, and then all 65 cans. So depending on which set you evaluate, just use the ascending order values for the set of data that you actually work with. So we'll go through an example with different values showing how to calculate the values that you need, but that's what you'll see if you download it. So now that we've gone through that part, what we're going to do is evaluate a little bit of notes for the experiment, just give a little bit of background for the experiment and information to know before you can do the evaluation. Okay. So as we go over a little bit of this, I'll just explain some of it because all the notes are available, but I wanted to make sure to evaluate some of these and explain it. So the primary consideration for this experiment is that there are two sources of variation in error that we're going to look at in this scenario. So there's experimental error and sample error. So for experimental error, those will be things that are inherently based on the experiment or those testing the experiment. So that could be two different testing machines, potentially with different calibrations, different observers testing different specimens, potentially the readings being read in different ways from those observers. It could also be any kind of discrepancy in one machine versus another. Additionally, you might have sample error, and sample error is inherently specimen differences. So specimen differences are primarily based on the item that you're testing. So in our case, aluminum cans. So that could be different manufacturers. It could be defects in the specimen. It could be any initial crack or bump or dent of any kind within the specimen. Given that there are no two specimens that are going to be completely 100% alike, then that's going to be any kind of specimen difference. So one thing to think about in terms of working with the experiment is which of those do you think is going to be more of an issue in terms of our differing values that we may get. Along with this, you may have two different plots that we're going to look at. So we're going to have distribution plots and we're going to have continuous plots. Distribution plots can also be described as a histogram. In that case, they look a little bit like bar graphs, but the spacing is taken out of that consideration. So in terms of the distribution plot, it shows the number of occurrences of a specimen within some particular range. So if we have, say, a 10-pound range, then you'd have 110 to 120, 120 to 130, 130 to 140, and so on. And then the number of cans that fell within each of those ranges would be synonymous with the number or height of each of the bars that's present within the histogram. So for continuous plots, these are often kind of looked at more as continuous plots, or normal distribution curves are often described as normal distribution curves. So with this, you may have a perfectly normal distribution, but you also may get a skewed distribution, which would be a positive or negative skew. So a positive skew would be a larger section in a higher prevalence earlier in your data set, with less in the tail end of your data set. So something like this might be if you organized all films that were made in, say, 2018, 2019, 2020, and ranked them from highest grossing film to lowest grossing film, and then did a distribution plot on individually each of those films with their grossing or gross number for their amount of money each made. So in terms of that, your highest films would be at the top, and then your tail end would be the films that made the lowest. So that would be a positive skewed set of data. So a negative skew would be where your highest values are more towards the end of your distribution. So in terms of that, it may be like retirement age. So you wouldn't really see as many people retiring at age 20 or 25, but you'd get a higher prevalence near the end of your curve at, say, 60, 65, or 70. So that would be a negative skewed set of data. You could also look at that from, say, a weight range. So weight as an infant to weight as an adult. That would start out very low and then be higher towards the end of your distribution. So for the mathematical representation of these values, we're looking at mainly four main calculations: average or mean, deviation from that mean, standard deviation, and variance. So for our average or mean, this is kind of the mathematical representation of it, but essentially it's adding up the value of each of your samples divided by the number of samples that you have. So if you had 1, 2, 3, 4, 5, and 6, then you would add 1, 2, 3, 4, 5, and 6 together and divide that by 6 as the number of samples or values that you have. For your deviation, in that case, what we're looking at is each individual sample minus the mean that you have. So if you had, say, a mean value of 3, that would be represented as your X bar. And if you were looking at, say, 1, 2, 3, and 4, your deviation would be 1 minus 3, 2 minus 3, 3 minus 3, 4 minus 3, and so on, depending on how many samples that you had. So the two that are kind of more mathematically intensive are the sample standard deviation and the sample variance. So there's sample standard deviation, and then there's population standard deviation, as well as sample variance and population variance. There are also a couple more ways to represent those, but those are the two that we're looking at in terms of this particular case. So for sample standard deviation, it's a measure of how spread out your numbers are when looking at a set of data. In this case, it's mathematically determined as your variance, or essentially the square root of your variance. So in this case, it's your individual sample minus the mean of your set of values divided by the number of samples minus 1. But just don't forget the square for your summation, because that's, in a lot of cases, sometimes left off. So I'll do an example of that, but I wanted to show the equations first. And then for your sample variance, it is the expectation of the squared deviation of a random sample with relation to its mean. So essentially we're looking at a random set of numbers and seeing how spread out those are. So to give a little bit of representation for the difference between our sample standard deviation or sample variance to our population standard deviation or population variance, essentially our sample variance is estimating the process in terms of sample data that's measured through that process. So another way you could look at this is your sample versions are looking at, say, a subset of a population. So if you had, say, 1,000, like a population size of 1,000, and you wanted to do a test on that but couldn't test all 1,000 samples, then if you wanted to test, say, 100 would be the sample set of your entire 1,000 size population. So mathematically that's represented as the population would have a denominator of n, which is your total number of samples, while your sample version would be n minus 1. So it's essentially taking a mathematical representation of not having the entire sample set for your data. So the sample version of this is often used in research because we're not looking at an entire population set, and a population set is a lot of times used in government. So for our example calculations, we'll go through average or mean, sample variance, and sample standard deviation. And then we'll also look at this in terms of Excel so you can see it with a set of data if you want to manipulate or work with your data using Excel. So for our example calculations, it's a little closer. Okay, so if our sample set of data is 1, 3, 5, 7, 9, and 11, so we have 6 numbers. So our average or mean will be the addition of these values divided by the number of values present. So if we add 1, 3, 5, 7, 9, and 11 together, we get a value of 36. So since there's 6 numbers present in this, we divide that 36 by 6, and our average value is, in this case, 6. With sample variance, we'll want to calculate variance before standard deviation because it just makes our standard deviation very easy to calculate. So in terms of this, it's the addition of your set of values divided by n minus 1. So if we're looking at 1, 3, 5, 7, 9, and 11 again, then we have our particular value, which will be either 1, 3, 5, 7, 9, or 11, and then the mean, which was calculated above as 6. So we have 1 minus 6 squared plus 3 minus 6 squared plus 5 minus 6 squared plus 7 minus 6 squared plus 9 minus 6 squared plus 11 minus 6 squared. And that'll be divided by our number of samples, which was 6 minus 1, because we're doing the sample case. If we were doing the population variance, then it would be divided by 6 instead of 5. So once we take the squares of each of these terms, then we get 25, 9, 1, 1, 9, and 25. If we add those values together, our numerator is 70. So with our value of 70, we then want to divide that by n minus 1, which would be 5. So then our sample variance in this case would be 14. So then after we have our variance, we can do our standard deviation. And essentially our standard deviation is just the square root of our sample variance. So in this case, I went ahead and worked out the entire version as if we didn't know the sample variance already. But considering we already do know the sample variance, which is 14, you could just take the square root of the value calculated as your sample variance, which would give you a sample standard deviation of about 3.7. I had a couple extra decimal places so you would see the continuation of that value, but essentially our sample standard deviation is approximately 3.7. So this shows some sample calculations if you were to do them by hand. May help out with other things that you have in the future, but this gives you some concept-based information on where those values come from. The next thing we'll do is look at a sample set of data and go through the Excel calculations, which will be the next part. So now we'll look at an Excel version of the calculations for the sources of variation in Error Lab. So we'll go through an example of what to do with the values that you've calculated. So in this example set, it's the example set from the historical data, but you can use the same process when going through your own set of data, depending on which set of data you work with. So in this case, we have 36 cans that were tested. So with these 36 cans that were tested, we have our peak load measurement that was found for each of those cans, and those same values ordered from smallest value to largest value. So once we have those values, we have everything we need in order to evaluate our data set for the items in our lab handout. So the first thing that we want to calculate is our average. So with our average, we can do equal to and type the word average, open parentheses, and then select all of the values tested for our set of data. So essentially all of the values in our peak load column. So our average then turns out to be 122.4353, and that gives us our average value. So once we have our average value, we can then calculate the two columns in the table that's in our lab handout. So for our deviation from mean, we have each of those values minus the mean that we have. So in this case, we can do equal to our first value for our load minus our calculated average value. So in order to get each of the values in our peak loads subtracted by the same average value, we need to essentially hold that average value for each of the values in this column. So in order to do that, we go in front of the letter for our average and put a $sign, and the number in front of our average and put a $sign. And that essentially just holds that value still. So we have a deviation from mean for our 148 pound load as about 26.551. So now there's this little green square in the column. So we can click that and hold and drag it down the whole column. So then that same formula will be attributed to each of the peak load values in our scenario. So that'll give us all of the values we need for our deviation from mean. Our squared deviation is just that deviation from mean value squared. So in order to find this, we can do equal to the first value of our deviation from mean and then do squared. So in this case, since we want each of those values squared, we don't have to do any kind of $sign to hold any kind of value because we want that value to change as it's being attributed to each of the values in our set. So now we can hold that same corner and drag it all the way down. And so now that has calculated all of our squared deviation values. So for our summation of deviation, we just want to add up all the values for our summation deviation values. So we do equal to sum And then we want the entire column that's the deviation from mean. So we just highlight this whole column. And we see we get a value of approximately 0. So why would we get an approximate 0 value when we add all those values together? So essentially the reason we're getting a summation of deviation value from 0 is once we calculate a mean or average. So once we get a summation of deviation value, then that value we want to see the average. So in terms of the average, the reason we're getting a deviation value of 0 is because we'll have essentially the same number of values above the mean as below the mean. And in this, if we take our deviation values that are positive values and our deviation values that are negative values, essentially they should even each other out approximately. So that's why we're getting a summation deviation value of 0. So next we look at standard deviation. So the way we want to find standard deviation, and in this case don't forget we're looking at sample standard deviation because we're doing a sample set of cans. So we're doing equal to stdev.s. So one thing you'll notice in these, you'll have stdev.p and stdev.s. So the p is population and the s is sample. So we'll take the standard deviation and we're looking at the standard deviation of that peak load value. So we can do all of our peak load values. So now we have our standard deviation term. So in order to determine our sample variance, then we want to calculate our variance value. So the reason this mean times number of samples values is given is that can be used to determine our check of variance. And I do that just to kind of show that you can get the variance value in two ways. So our mean times number of samples, we'll just do equal to, and it's our average value multiplied by the number of samples that we have, and we have 36 samples. So our mean times number of samples values is approximately 4,407. So now that we have those values, we're looking at our variance. So in this case, we're looking at, again, sample variance. So we have equal to var.s. So there's var.p and var.s. So if we're looking at variance for our sample set, then we do var.s, and then we have peak load. So now we get our variance value as approximately 1,328.7. So we only have a few values left in terms of the values that we need for our handout. So one of the values at the bottom of the table, so there's a couple blanks at the bottom of the table, one of the values there is doing the sum of squared deviation, so essentially the sum of that column in the table. So our sum of squared deviation would be equal to sum of this column that's our squared deviation. So we have a sum of square deviation value of 46,504.5 approximately. So the last numerical value that we want to do is our check of variance, and this is mainly just to give us a representation to make sure that we've checked our variance correctly and that it follows the same equation in terms of the sample versus population set. So our check of variance will use our sum of square deviation, so we can do equal to our sum of square deviation divided by our number of samples, which is 36 minus 1. And that gives us 1,328.7 approximately, which is the exact same value the Excel calculated value gave us. So that completes our calculated values that we need for our lab handout. So now we have our graphical representation of our set of data. So we can do one of those two different plots that we talked about earlier. We can do a distribution plot or a continuous plot. So the first one we can do, we'll just do the histogram plot first because that one we don't have to do any kind of other calculation. We can highlight our peak load column. So we'll highlight all 36 values. We can go to Insert and select a histogram plot. So in this case, we have a histogram type plot. Make it a little larger. So we can add chart elements, so we can add a title. We can add axis titles. And then change these names. So like number of occurrences. And then add a horizontal label, which is our load value. We can also add a representation of how many cans are in each of those. So we can do data labels and add them on the inside, outside, outside end, wherever you want to place them. So the next thing that we can do is, if we don't like the representation of how this is attributed, then we can change the appearance of our graph. So one way to do this is if you click on the load region distribution here, you can right click it and it'll give you a format axis option. So in this, it gives you the opportunity to evaluate or change how you separate your categories of your separation. So the way that I usually like to do it is I take the standard deviation value that we calculated and use that as a distribution for the underflow and overflow. So I take the average value and subtract the standard deviation, and that's my underflow bin. And I take take the average and add the standard deviation and make that my overflow bin. And then that gives me kind of a normal distribution for my histogram. So if I click these overflow and underflow bins, then I can look at the approximate values for where I want to make those. So if it's 122 plus 36, then that's around like 158. So I can do, say, an overflow bin at 158. And then if I do underflow, like 36 minus 22, we'll just kind of estimate. So we'll say our underflow bin is around 85. So now you see the distribution gets a little bit different. So you can also change how you want these represented. You could say you want the range to be, say, 10 pounds each, and you'll get a lot more bins. Or you can change the number of bins to, say, 5. So then you'd get 5 columns. So you can change the representation of this. And I kind of like the 5 bin, so we'll just leave that how it is. You can also label this as histogram. So if you choose to do the histogram graph, then you can turn that in, and that'll be your histogram graph, and you're done. So if you want to do the continuous plot, we'll do the representation for that to show it. So in this, we need this normal distribution column and those ascending values. So for this, there's a value built into Excel called norm.dist. So if we do norm.dist, then it'll ask for 4 main values. So the values that it wants are the individual value that we're looking at that particular time, in that case, your smallest value. Then it wants your mean or your average, so then we give that. And then it wants our standard deviation, so we list that. And then it wants what's called a cumulative, and I'll explain this in just a second, but you can either do it as true or false, or 0 or 1. So in this case, we'll do 0, and I'll show you what that looks like, and then we'll do 1, and I'll mention the difference. So once we have that defined, then we have our equation for our normal distribution. So the other thing we need to set in this is our average and our standard deviation values do not need to change in each of these columns. Those are just a single cell. So in this, we want to go back in and do a $sign in front of the letter and the number for mean, and a $sign in front of the letter and number for standard deviation. Now we can take this and drag this for the whole column. So now we have normal distribution values for the whole column. So now if we want to graph this, so we can highlight this whole column, highlight both of these, and then do a scatter plot. And you'll see it looks like a fairly reasonable normal distribution plot. So it's a little bit skewed. It's not directly in the center because we have these little outliers over here. but it's fairly normal distributed for the set of cans that we have. So in terms of this, we have our normal distribution curve. So from this is from doing the value at 0. And in terms of this will be what's called a normal probability density function. And that essentially gives us a representation of like a bell curve type appearance. So it's fairly similar to a histogram in terms of the information you can get from it. It shows the ranges or values that occur and how often those occur. So if I move this out of the way and change the value to 0, or sorry, from 0 to 1, I'll show what the change is. And in this case, when you do a 1, it'll be a cumulative normal distribution function. And what changes is how that data is represented. So if we change that to 1, then you'll see it looks more kind of parabolic in appearance to start with. Well, not really parabolic, but it's kind of more like a logarithmic type graph, or like exponential. So I guess exponential is the best representation. So you get more of kind of a distribution up to 1. So what's happening in this case is 1 is all of your cases, and the points that are represented are the prevalence of those values up to 100%. So when you're at, say, 0.6, then 0.6 and below is how many points you have at 60% of the values that you're looking at. So at 150 pounds, then at that point, at this point here, so it's like roughly 122 pounds, which was our mean. So around 50% would be our 122 pounds. So we have about half the values below it. At that 122 pounds, would have half the values above it. So at 60, would have 60% of the values under and 40% of the values above. So that's a cumulative normal distribution, not a normal probability density function. So now we can go back and change this to 0. And you'll see it looks back like our normal probability density function curve. So this represents the difference between the normal distribution that you can get in terms of just changing that one cumulative value, and this will be the representation of what the calculated values are. So after you have all of your mathematical represented values, then you answer the questions and add a discussion based on the information you found from your data set and what you found in terms of the information prior to the experiment, after the experiment, and your evaluation. Anything that you wish you would have found out and didn't, things that you might think you could extend the experiment, anything like that could be included in your discussion. And you can also add the labels and axis titles on this graph, and that'll be the completion of the assignment. So hopefully this example helps, and this will be the main section. So if you need to look at the experimental video, then that is available in an extra video.